крайней мере, самый простой план. So our plan for today. Would be to prove the localization theorem first, and then I'll briefly mention other types of localizations and what they're good for. Well, first of all, let's briefly recall the theorem itself. Part 1 says that every abelian space has a Q localization. Part 2 a map of abelian spaces is a Q localization if and only if the reduced homology of X prime, the target space is a Q vector space, and the map of the reduced homology of X tensor Q to the reduced homology of X prime. Sorry, I don't need the Q coefficients here. I can just write integral homology. So this is a Q vector space. This is a Q vector space, and we have a map from this one to this one, and the condition is that this map should be an isomorphism. Part 3. suppose we have this diagram of abelian spaces where the horizontal arrows are Q localizations. The left vertical arrow is just some continuous map. Then there exists an F prime which makes the diagram commute. The F prime is unique up to homotopy, and or more precisely, there is a unique F prime up to homotopy, which makes the diagram homotopy commute. So everything is homotopy in this statement. There is a way to make localization a functor on the level of spaces, but we'll talk about that later. Okay. Does everything on the blackboard make sense? If someone doesn't remember what an abelian space is, or what the Q localization is, please let me know. Here's the plan for proving the theorem. We'll first prove this implication for part 2, then we'll prove part 1, then we'll prove the reverse implication for part 2, and then we will prove part 3. Okay. Are there any questions, objections, and so on? Okay, so let's prove part 1/2 of part 2. If we have a map which is a localization, then the integral homology is Q local, which means it's a Q vector space, and the map reduced homology tensor Q to reduced homology of X prime is an isomorphism. Well, first of all, let's observe that for every abelian group, the map pi, the map from k pi n to k pi tensor q n is a localization, is a Q localization. which is basically straightforward from the definition of the Q localization. Okay, well, but this doesn't mean that we know anything about the homology of either of these spaces. The homology and cohomology of K pi n is complicated. It's manageable, tractable, but it's complicated, and we will see in a minute that the homology of Qn is is a free algebra on one generator, which makes it very simple. But still, we need to prove the statement, the implication. And we start with K pi 1, and we first consider the case when pi is finitely generated under Boolean. Well, K pi n is a functor of pi. So there's for each map of groups, there is a unique homotopy map of the K pi n's. Okay, so we start with K pi 1, and the claim is well, firstly, for K pi 1, we know the localization, and we only need to check the conclusion. Let's start with pi equals z. KQ1 is a telescope. Of the following sequence of maps. I take all spaces to be S1, the circle, and the maps to be basically any sequence of maps which contains all integer numbers greater than or equal to. Basically, the simpler solution would be to just take every number once, and we will get what we're after. So before we continue, does everyone remember what the telescope is? No. Okay. So well, in brackets. If the word homotopic co-limit makes anything clearer, then it's just the homotopic co-limit. But let's draw a picture. Ну, буквально, но значит, кому-то ближе телескопа, кому-то ближе микроскопа. Поэтому, в общем, на всякий случай два альтернативных термина. Okay, just a brief reminder. So suppose I have x1, x2, x3, and so on. An infinite sequence of spaces and a map from each space to the next. I can take the telescope to be the union of the cylinders. I first take the cylinder of x1 to x2, then the cylinder of x2 to x3, and so on. The cylinder of x1 to x2 contains both x1 and x2, and the cylinder of x2 to x3 contains x2 and x3. Well, I can identify the two copies of x3, and I get the first stage of the telescope. And then I continue. Does this picture make sense? Okay, so basically the pi 1 of this thing is the direct limit of this sequence of groups and group homomorphisms. So it's pretty straightforward to check that the sequences, the limit of the sequence is Q. And similarly, the higher homotopic groups vanish for essentially the same reason. For each each finite stage of the telescope is the last space in the telescope. So the all spaces are circles. So the higher homotopic groups are zero. Does this argument make sense? Good. Okay. So for KQ1 is indeed a telescope. Now we we want to prove this this part. We want to prove that the homology of this thing is Q-local. Well, it is Q-local because for homology we have the same formula. Homology and homotopy groups commute with direct limits of spaces. So the H1 of the space is Q. Now we want to prove that this map is again is an isomorphism, which means we want to prove that if we take the map from Z to this limit or co-limit, we get just the map, the standard inclusion of Z into Q. This is straightforward. Actually, one way to think about this co-limit would be to view it as Z inside 1/2 Z inside 1/6 Z, and so on. If you look at this sequence of inclusions, it's precisely this one. Does this make sense? Okay, so the union of 1 over n degree Z, and so the map of the first homotopy groups is just the inclusion of Z in Q. Does this make sense? Okay, so for pi equal Q and for n equal 1, we did prove what we're after. Just using an explicit construction of k something of kq1. Okay. Okay, I will erase part 3. We'll write it again when we need it. Okay, well, let's now take pi equal Z by m, and well, pi tensor Q is 0, and my claim is the integral homology of k pi 1 is torsion, and moreover is M torsion, meaning all orders of elements are divisible divisors of M. Okay. Does anyone know why? In general, if we have a finite group, then all homology and cohomology groups of the k pi 1 are torsion, and the order divides the order of the group. Let's see why this is true. Well, yes. One way to proceed would be to consider the universal cover, which has a finite number of sheets, and the number is M. But then what do we do? There is the so we have okay. So so we have the universal cover, which is contractible, and there is the map. There is a map from the cohomology of this space to the cohomology of this space, which is the usual pullback, and there is also the map in the opposite direction, which is called the transfer map, and we can compose the two, and we get multiplication by M. By the way, where does the transfer map come from? Let's call this P upper star, the transfer, and if I first pull back, then take the transfer, I get M times id, where M is the number of elements. Oh, well, but where does this map come from? Does anyone know? Yes. How to define this map?
So we can take singular simplex in the base, and then sum of its widths.
Okay. So one explicit idea would be to we need a map which goes in the wrong direction. So I have so So for sorry, what's your name? So Andrei is proposing to construct the map in the wrong direction, but for homology. And we start with the simplex here, and we take it to the sum of all of its lifts here. Is this what you're proposing?
Yes, so we get map on a singular chain, so we can make the map on singular cochains.
Okay. Well, yes. This is one of the ways to describe this map. Another way to describe the same map would be to take the constant sheaf on this space, pull it back, then push forward, and then we have an junction map from the push forward of the pullback into the sheaf itself. By the way, is it the unit or the co-unit of their junction? Well, since it's a natural transformation from something to the identity, it's the co-unit. Okay, so we have this map. Okay, so this is P. We have this map of sheaves. Okay. Well, the pullback of the constant sheaf is the constant sheaf. There's no surprises there. Now, the map is a covering map. So all higher cohomology, all higher direct images of this sheaf vanish. So the derived direct image is the same as the usual direct image. So this sheaf actually calculates the cohomology of this thing. And this sheaf calculates the cohomology of this thing. So we get a map from the cohomology of this thing into the cohomology of this thing, which is a transfer. If none of this makes any sense whatsoever, let's just forget about sheaves, because sheaves is sheaf theory is an important and useful thing, but we don't really in this seminar we're more preoccupied with other things. Anyway, so we have this map. Why? How does this imply that the cohomology of K pi 1 is M torsion? We have the pullback, the transfer. The composition is multiplication of the order of the group. What next? factors.
Yes, factors.
Yes. So let's look at this formula. We want to prove that all parts of dimension greater than 1 is 0. Okay. We apply the left-hand side of the formula. We take the pool back, we get something, but this something lives in the cohomology of k by 1, which is 0 in all degrees greater than 1, greater than or equal 1. So and then we apply TR, whatever this is, we arrive back where we started. Okay, does this argument make any sense? So basically, the only thing we use is that there is this transfer map, and the transfer map is a kind of an inverse to P upper star, but not really. The composite is not identity, it's M times identity. Okay, so and then how to construct the transfer map? Well, Andrei just gave one construction, and if there are people who prefer sheaves, well, there is the construction from the adjunction co-unit for sheaves. Are there any questions? So we proved this implication for phi equals z by m, and n equal 1. Okay. My claim is then every group every abelian group is the direct limit of its finitely generated subgroups. No surprises there. So for finitely generated groups, we just use the Kunis formula, and for an arbitrary phi, we use the fact that basically homology and homotopy groups commute with direct limits. For example, suppose we know that suppose we have some sequence of or some family of subgroups of phi, and we know that the homology of something with coefficients in each of those is a Q vector space, then the direct limit is again a Q vector space. The direct limit of abelian groups which are Q vector spaces is a Q vector space. the direct limit is exact, so the direct limit of isomorphisms is an isomorphism. We don't need exactness of the direct limit here. The direct limit is a functor, so it takes isomorphisms to isomorphisms. But then we, in order to get the direct limit of abelian groups, we need to check that homology commutes with direct limits. Anyway, does this blah blah suffice, or do I need to explain this part in more detail? Sorry. More detail. Okay. So phi is the direct limit of sigma every group is the direct limit of its finitely generated subgroups. Every abelian group is the direct limit of its finitely generated subgroups. So we well, firstly, we have k pi 1 is the direct limit of k pi k sigma 1. To claim this, I need some kind of a functorial strictly functorial construction for k pi 1, but those exist. Okay, so the localization, as we know, is k pi tensor q 1, which is the direct limit of sigma tensor q. To see this, we firstly prove the same result on the level of groups, and then we use a strictly functorial k pi 1. Okay, then I have what do I need to prove? Firstly, I need to prove that this is a Q vector space. Homology commutes with direct limits. So the homology of the direct limit is the direct limit of the homology groups, and each of those is a Q vector space. So the homology is itself a Q vector space. And similarly, I need to check that this map is an isomorphism. Well, it's the direct limit of isomorphisms that we have for each individual sigma, and so it's an isomorphism. Do we want more details? Good. Okay, so now I need to. I have proved something for k pi 1, and I need to prove the same for k pi n. Well, luckily this is more or less formal, but here we will assume we know all about spectral sequences. So we have proved the implication, this implication for k pi 1s, where pi is an arbitrary abelian group. Now we need to prove the same for k pi n's, for an arbitrary n. How to do this? Well, we will use the following thing. Suppose we have a homologically trivial. I will explain what it is. Homologically trivial self-vibration FEB. If 2 of 3 2 of the 3 groups the homology of F, the homology of V, the homology of P are Q vector spaces, so is the third. Now, I need to explain what exactly I mean by homologically trivial vibration. With all coefficients z by m, where m is an integer greater than or equal to. With all finite coefficients. Well, let's to see what this means. Let's recall the the following thing. The fundamental group of the base acts up to homotopy on the fiber, which means every loop in the base induces a self-map of the fiber, which is not well defined, but it is well defined up to homotopy. This is basically straightforward from the definition of the CF vibration. So, in particular, we get a genuine action, no homotopy on every homology and cohomology with any constant coefficients, and this is the action we need for this condition. F vibration is homologically trivial. For all finite coefficients. Does this make sense? And to prove the lemma, we need two observations. Or basically just one observation. The reduced homology of X with z coefficients is a Q vector space if and only if the reduced homology of X with all finite coefficients is 0. Now, this is what it says, but is it true? And if it is true, then why? И что? В Z тоже нет кручения. Но Z практически поле.
Если по одному такое, то существовало гомологии, с гомологией, в общем, формулу вы сами хотите, короче, можно воспользоваться и все.
Окей, нет. Ну, или нет, здесь So the integral homology of x is in Q vect if and only if multiplication by every m greater than or equal to is invertible. In all abelian groups, we can multiply by every m. But in general, the result will not be injective or surjective or neither. Okay, so we want to see when multiplication by m is invertible in this group. We use this exact sequence of the coefficient groups. So this assertion is equivalent to saying that the reduced homology of x mod m is 0 for all m greater than or equal to. Does this make sense? So a short exact sequence of the homology of the coefficient groups induces a long exact sequence of the homology groups, and every third map is an isomorphism if and only if every third group is 0. Okay, and basically here we just once we know this, we apply the Serre spectral sequence, and this proves the lemma. The Serre spectral sequence in order for the Serre spectral sequence to have the expected form, we need this condition that the vibration should be homologically trivial, because otherwise the Serre spectral sequence becomes more complicated. Again, do we want more details on this part? I don't want to say too much about spectral sequences. It's a very useful tool in topology, and there is a course on spectral sequences which takes place right after this one. So in this course, you will learn all about spectral sequences. But if there are people who would like me to remind themselves of a thing or two, I will do this. So let's assume that we're all more or less familiar with spectral sequences and just use the lemma to prove well, at least let's finish the proofs for k by n's. Or do we want to have a break first? Okay, so let's erase everything apart from the lemma and have a break. Let's have a 20-minute break as usual, and then today we'll, as I said at the beginning, today we'll finish slightly earlier. And by the way, have you written to Vasya? Что? Не ответил. Ну хорошо.